So I chose to break this problem down into 3 parts. In the first part, the block is moving from exactly the center where it's just hit the timer over to the spring. In the second part, it's in contact with the spring, compressing it, and then finally extending again. And in the third part, the block is moving to the right, back towards the timer. Note that this problem is completely symmetrical, so it's sufficient for me to solve the problem on one side, and I know the same thing is going to happen on the other side. So I only need to solve for one period of the block moving over here and bouncing back to the timer, and I know the same thing is going to happen on the right side. So in the first part, the block needs to travel a distance of 1.5 meters, and it's going at a velocity of v0. So I'm going to use this kinematics equation here, and I know that the acceleration is going to be 0 during this part, so I can cross out this term. And doing a little algebra and plugging in my values here, I find that the time it takes for the block to move this distance of 1.5 meters is equal to 1.5 over v0. So I'm actually going to skip part 2 for a second and move on to part 3. And in part 3, we said that the block is moving to the right and needs to cover the same distance of 1.5 meters again. And we know from conservation of energy that the kinetic energy of the block has to be the same both before and after it makes contact with the spring, which means that its speed will actually remain the same both before and after, since the mass is remaining the same. This means that part 3 is actually an exact mirror image of part 1. The block is just moving to the right this time over a distance of 1.5 meters at this same speed, v0, except this time it's to the right. So we can actually conclude right away that the time for part 3 is just equal to 1.5 over v0, just like part 1. Now what about part 2? Well, I made the argument in the question that the time that the block stays in contact with the spring is actually equal to 1/2 of the period, not the full period of the oscillation of the spring. And this is because at this point, the spring is just about to pull back on the block, but because the block isn't attached, the spring can't actually pull back on the block. So the block is free to move with the same velocity it has at this point, which happens to be the maximum velocity, as well as the velocity that the block started with when it was coming in, v0. So we can say that for part 2, the time it takes is simply equal to the period of the oscillation over 2. All right, now let's put these 3 times together. So if we add together these 3 times and substitute in the period for the oscillations of a spring, we get this equation for the time it takes the block to move away from the timer and return back to it. And we know we want this time to be equal exactly to 1 second. And solving this equation for v0, I get that the original speed should be equal to 1.08 meters per second. Great job.